Okay, let's look at this Doppler effect question from February-March 2018. It says, a police car is moving at a constant speed on a straight horizontal road. The siren of the car emits sound of a constant frequency. Each of the two observers, A and B, standing some distance apart on the side of the road, records the frequency of the detected sound. Observer A records a frequency of 690 Hertz, and observer B records a frequency of 610 Hertz. State the Doppler effect in words. So that's an apparent change in the observed frequency as a result of the relative motion between a source and an observer. Okay, so we've got two stationary observers here and a moving police car. You can see that this one, observer A, has got a high frequency, okay, and observer B has got a low frequency. So this means if you have a high frequency and you're standing still, the car has to be moving towards you, because remember, you're pushing out the sound waves and they appear to be getting closer together, whereas behind you they appear to be spreading out. Okay, so the car has to be moving towards A because the sound has a higher frequency. So the sound has a higher recorded frequency. Whoops, scribbling over the other thing. Now it says determine the speed of the police car. Take the speed of sound in air as 340 meters per second. So okay, let's just do 6.4. Name one application of the Doppler effect. That would be something like a fetal heart rate monitor, or the Doppler flow meter, something like that. Okay, let's go back to this question here. Determine the speed of the police car. Now the problem is, here is my frequency of the source, okay, but we don't know it. Here is a frequency of a listener A, and here is the frequency of a listener B. And so we don't know the frequency of the source, and we don't know the velocity of the source, because remember, this is our Doppler equation. The frequency of the listener is a fraction. You hear a fraction of the frequency of the source, and if it's coming towards you, it's an improper fraction, and if it's going away from you, it's a normal common fraction where the top is small and the bottom is big. So it looks like we have to make a simultaneous equation to solve this, and it's 6 marks, so it's not just substituting into a formula. So let's go here, let's look at observer A. So for observer A, we write out the formula. The frequency of the listener equals V plus or minus the velocity of the listener over V plus or minus the velocity of the source multiplied by the frequency of the source. So for observer A, they heard 690 Hertz. This velocity of sound is 340. The listener is standing still, so we're adding nothing. And now this sound is louder, so we want to subtract the velocity of the source. So it's 340 minus the velocity of the source times by the frequency of the source. So before we go, we're going to form equation 1 from this for our simultaneous equation. But before we go any further, let's see what the other one looks like. So if we look at observer B, okay, we're going to use the same formula. The frequency of the listener equals the velocity of sound plus or minus the velocity of the listener over the velocity of sound plus or minus the velocity of the source multiplied by the frequency of the source. So the one here, observer B, heard at 610. The speed of sound is 340. The velocity of the listener is nothing. And now this will be 340 plus the velocity of the source, which is what we're trying to find, and then the frequency of the source. So we're trying to find the frequency of the source. We're trying to find the velocity of the source, because that is the speed of the police car will be the velocity of the source. So what we should do with our equation here is we should make it equal to Fs. Okay, so if we take this equation, and I don't have space down there, so I'm going to come up here. If I say 610 and I multiply by the denominator on that side, 340 plus Vs, Okay, over 340 plus 0 is 340. This is going to be equal to the frequency of the source. That'll be my equation 1. And if I come back to observer A, I can do the same thing here. 690 multiplied by the denominator on the other side, because algebra, over 340 plus 0, which is 340, is going to be equal to the frequency of the source. And this is my equation 2. So now they're both equal to the frequency of the source. So I can say 610 multiplied by 340 times Vs over 340 plus Vs, sorry, equals 690, 340 minus the velocity of the source, which we're trying to find, over 340. My two equations are equal, and they're both equal to the frequency of the source. So now we're dividing both sides by 340, so I can scratch that out, okay? And then I end up with here, what will I end up with here? 340 plus Vs will be equal to 690 over 610 multiplied by 340 minus Vs. So this 690 divided by 610, I can get a value for it, okay, if I put it in my calculator, and then I end up with it something like 1,131 or something, okay, times 340 minus Vs equals 340 plus Vs. So now the Vs and this one, they're going to be like terms, so you can solve this equation and you end up with the velocity of the source being 20,92 meters per second. So at some stage, most of your marks, you must realize that if you're going to look for your marks, most of your marks come from setting up these two equations, knowing where to put the frequency of the source and the velocity of the source. So if you get stuck with solving the simultaneous equation, just know you're going to get your mark for the formula and you're going to get the mark for setting these ones up, and very few marks for solving. So then you should be fine with the equation.